The National Electrical Code, or NEC, dictates the rules for paralleling conductors, influencing the number of conductors allowed in a conduit based on its size and the conductor's ampacity. To determine the correct conduit size and number of conduits, we must refer to NEC Table 310.15b3. This table provides a formula to calculate the maximum number of conductors permitted in a single conduit. The formula is number of conductors equals 1 plus conduit area divided by conductor area, where conduit area represents the cross-sectional area of the conduit, measured in square inches, and conductor area is the cross-sectional area of the conductor, also in square inches. Let's apply this to a scenario involving 500 mcm conductors. The conductor area for a 500 mcm conductor is 0.503 square inches. Using the formula, we get 1 plus conduit area divided by 0.503. To meet the NEC requirement, the result should be that the conduit area must be at least 2.99 square inches. The standard conduit size that meets or exceeds this requirement is 4 inches. Now, to calculate the number of conduits needed, we use the formula again, this time solving for the number of conductors allowed per conduit. Number of conductors per conduit equals 1 plus conduit area divided by conductor area, which translates to 1 plus 4 divided by 0.503. This equals 9. If you need to install 24 conductors in total, you would require at least 3 conduits. This is because 24 conductors divided by 9 conductors per conduit equals 2.67, which rounds up to 3 conduits. When dealing with electrical installations, directing of wire is another factor to consider. Directing is typically implemented when conductors are exposed to high ambient temperatures, which reduces their ampacity. In situations where high ambient temperatures are not a factor, directing may not be necessary. In summary, based on NEC requirements and calculations, a minimum of 3 conduits, each containing 4 500 mcm conductors, is needed to meet an 800 amps demand. This configuration can lead to significant cost savings compared to using 6 conduits each with 4 500 mcm conductors. To ensure compliance with the NEC and other relevant codes, it is advisable to consult with a qualified electrician to review calculations and installation plans. This can help to avoid potential issues and ensure a safe and efficient electrical system. When dealing with electrical installations, understanding and correctly applying the National Electrical Code, NEC, is crucial for safety and compliance. Let's delve deeper into several key aspects, including conductor ampacity, conduit fill directing, and voltage drop. Firstly, conductor ampacity refers to the maximum current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. The NEC provides tables, such as Table 310.15b16, that list the ampacities of various conductor sizes and insulation types based on temperature ratings. Selecting the appropriate conductor size ensures that the wiring can handle the intended load safely. Secondly, conduit fill is another essential factor in electrical installations. It refers to the percentage of the cross-sectional area of a conduit that is occupied by conductors. The NEC specifies maximum fill percentages to prevent overheating and ensure easy wire pulling. For example, for 3 or more conductors in a conduit, the maximum fill percentage is typically 40%. Exceeding this limit can lead to heat buildup and potential insulation damage. Thirdly, directing is the reduction of a conductor's ampacity due to factors such as high ambient temperature or the presence of multiple conductors in a conduit. The NEC provides tables, such as Table 310.15b3, that specify directing factors based on the number of current carrying conductors in a raceway. For example, if there are more than 3 current carrying conductors in a conduit, the ampacity of each conductor must be reduced by a certain percentage. Directing ensures that conductors do not exceed their temperature ratings under various conditions. Fourthly, voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 5% for feeders and branch circuits. To calculate voltage drop, you can use Ohm's law and the conductor's resistance per unit length. Selecting larger conductors or shortening the length of the circuit can reduce voltage drop. When sizing conductors and conduits, it's important to consider these factors collectively. Start by determining the load requirements and selecting conductors with sufficient ampacity. Then calculate the number of conductors needed and select a conduit size that complies with the NEC fill requirements. Apply any necessary directing factors to ensure that the conductors can handle the load under the given conditions. Finally, check for voltage drop and make adjustments as needed to ensure that equipment operates within acceptable voltage limits. Here is an example. Suppose you need to install a 200 amps feeder to supply a subpanel located 100 feet away. The conductors will be installed in a conduit with 6 other current carrying conductors, and the ambient temperature is 30 degrees Celsius. Firstly, determine the conductor ampacity. According to NEC Table 310.15b16, a 3/0 AWG copper conductor with THHN insulation has an ampacity of 200 amps at 30 degrees Celsius. Secondly, check conduit fill. Suppose you are using 1-1/2 inch conduit and need to run 3/0 AWG conductors. The NEC allows a maximum fill of 40% for 3 or more conductors in a conduit. The total cross-sectional area of the 3 conductors is less than 40% of the conduit's area, so the conduit size is adequate. Thirdly, apply directing factors. Since there are 7 current carrying conductors in the conduit, you need to apply directing factors from NEC Table 310.15b3. For 7 to 9 conductors, the directing factor is 70%. Therefore, the adjusted ampacity of the 3/0 AWG conductors is 200 amps times 0.70, which equals 140 amps. Because 140 amps is less than 200 amps, you must increase the conductor size to compensate for the directing. According to NEC Table 310.15b16, a 4/0 AWG copper conductor with THHN insulation has an ampacity of 230 amps at 30 degrees Celsius. After applying the 70% directing factor, the adjusted ampacity is 230 amps times 0.70, which equals 161 amps, which is still less than 200 amps. You need to increase the conductor size again. According to NEC Table 310.15b16, a 250 kcmil copper conductor with THHN insulation has an ampacity of 255 amps at 30 degrees Celsius. After applying the 70% directing factor, the adjusted ampacity is 255 amps times 0.70, which equals 178.5 amps, which is still less than 200 amps. You need to increase the conductor size again. According to NEC Table 310.15b16, a 300 kcmil copper conductor with THHN insulation has an ampacity of 285 amps at 30 degrees Celsius. After applying the 70% directing factor, the adjusted ampacity is 285 amps times 0.70, which equals 199.5 amps, which is still less than 200 amps. You need to increase the conductor size again. According to NEC Table 310.15b16, a 350 kcmil copper conductor with THHN insulation has an ampacity of 310 amps at 30 degrees Celsius. After applying the 70% directing factor, the adjusted ampacity is 310 amps times 0.70, which equals 217 amps. The adjusted ampacity is greater than 200 amps, so you can use 350 kcmil copper conductors with THHN insulation. Fourthly, check voltage drop. To calculate voltage drop, you can use the formula voltage drop equals 2 times K times I times D divided by Cm, where K is the constant for copper 12.9 ohms, I is the current in amps, D is the distance in feet, and Cm is the circular mils of the conductor. The circular mils for a 350 kcmil copper conductor is 350,000. Voltage drop equals 2 times 12.9 ohms times 200 amps times 100 feet divided by 350,000, which equals 1.47 volts. The percentage voltage drop is voltage drop divided by voltage source times 100. Assuming a 240 volt source, the percentage voltage drop is 1.47 volts divided by 240 volts times 100, which equals 0.61%. This is well below the NEC recommended maximum of 5%. Therefore, a 350 kcmil copper conductor with THHN insulation is adequate for this installation. Keep in mind that this is a simplified example, and actual installations may require additional considerations such as grounding and bonding requirements. Always consult with a qualified electrician and adhere to the NEC and other applicable codes to ensure a safe and compliant electrical system. In addition to the previous considerations, it's essential to understand the concepts of conductor insulation types, grounding, and bonding. Firstly, conductor insulation types are crucial for ensuring safety and preventing electrical hazards. The NEC specifies various insulation types for conductors, each with different temperature ratings, moisture resistance, and other characteristics. Common insulation types include THHN, THW, and XHHW. THHN insulation is commonly used for dry locations and has a maximum temperature rating of 90 degrees Celsius. THW insulation is suitable for wet locations and has a maximum temperature rating of 75 degrees Celsius. XHHW insulation can be used in both wet and dry locations and has a maximum temperature rating of 90 degrees Celsius. Secondly, grounding is a critical safety measure in electrical systems. Grounding provides a low impedance path for fault currents to flow back to the source, tripping the circuit breaker or fuse and preventing electrical shock hazards. The NEC requires grounding of electrical systems and equipment to ensure safety. Grounding electrodes, such as ground rods or metal water pipes, are used to connect the electrical system to the earth. Thirdly, bonding is another essential safety measure that involves connecting all non-current carrying metal parts of an electrical system to create a continuous electrical path. Bonding ensures that all metal parts are the same electrical potential, reducing the risk of electrical shock. The NEC requires bonding of metal conduits, enclosures, and equipment to maintain electrical safety. When installing electrical systems, it's crucial to follow the NEC requirements for conductor insulation types, grounding, and bonding. Using the correct insulation type ensures that conductors can withstand the operating conditions without degrading or failing. Proper grounding provides a safe path for fault currents, protecting people from electrical shock. Effective bonding minimizes the risk of electrical shock by ensuring that all metal parts are at the same electrical potential. Here is another example. Suppose you are installing a 120/240 volt single-phase service to a residential building. The service entrance conductors will be installed underground in a conduit. Firstly, select the appropriate conductor insulation type. Since the conductors will be installed underground in a conduit, you should use conductors with insulation suitable for wet locations. THW insulation is a common choice for this application because it is rated for wet locations and has a maximum temperature rating of 75 degrees Celsius. Secondly, establish grounding. The NEC requires grounding of the electrical service to provide a low impedance path for fault currents. You can use a ground rod or a metal water pipe as the grounding electrode. Connect the grounding electrode to the service equipment using a grounding electrode conductor. Thirdly, ensure bonding. Bond all metal parts of the electrical system, including the service equipment enclosure, metal conduits, and any other metal enclosures. Use bonding jumpers to connect these metal parts together, creating a continuous electrical path. By following these steps, you can ensure that the electrical system is properly grounded and bonded, minimizing the risk of electrical shock and providing a safe electrical environment. Remember to consult with a qualified electrician and adhere to the NEC and other applicable codes to ensure a safe and compliant electrical installation. To further elaborate on the NEC and its impact on electrical installations, it is crucial to understand the role of overcurrent protection, arc fault circuit interrupters, and surge protection devices. Firstly, overcurrent protection is a fundamental aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current, which can cause overheating, insulation damage, and fire hazards. The NEC specifies the maximum allowable overcurrent protection for various conductor sizes and equipment. When selecting overcurrent protection devices, it's essential to choose the correct size to protect the circuit without causing nuisance tripping. Secondly, arc fault circuit interrupters, or FSIs, are devices that detect arc faults, which are dangerous electrical conditions that can lead to fires. Arc faults occur when electricity jumps between conductors or to ground, creating heat and potentially igniting nearby materials. The NEC requires FSIs in many branch circuits in residential buildings, particularly in bedrooms and other living areas. FSIs provide an additional layer of protection against electrical fires by detecting and interrupting arc faults before they can cause damage. Thirdly, surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges, which are sudden and temporary increases in voltage. Voltage surges can damage sensitive electronic equipment, such as computers, televisions, and appliances. SPD divert excess voltage away from the equipment, protecting it from damage. The NEC recommends the use of SPD in electrical systems to protect against voltage surges caused by lightning, utility switching, or other sources. When installing electrical systems, it's crucial to incorporate these safety measures to protect people and property from electrical hazards. Overcurrent protection prevents overheating and insulation damage. FSIs detect and interrupt arc faults, and SPD protect against voltage surges. Here is an additional example. Suppose you are wiring a new kitchen in a residential building. The kitchen will have several branch circuits for lighting, receptacles, and appliances. Firstly, provide overcurrent protection. Each branch circuit should have its own circuit breaker or fuse to protect against overcurrent. Select the appropriate size overcurrent protection device based on the conductor size and the load requirements of the circuit. For example, a 15 amp circuit may use 14 AWG wire, protected by a 15 amp circuit breaker. Secondly, install FSIs. The NEC requires FSIs in all 120 volts, single phase, 15 amps and 20 amps branch circuits supplying outlets in kitchens. Install FSIs to protect against arc faults and reduce the risk of electrical fires. Thirdly, consider surge protection. To protect sensitive electronic equipment, such as appliances and computers, consider installing a surge protection device at the service entrance or at individual branch circuits. SPD can help to prevent damage from voltage surges and prolong the life of electronic equipment. By incorporating these safety measures, you can create a safe and reliable electrical system in the kitchen. Remember to consult with a qualified electrician and adhere to the NEC and other applicable codes to ensure a safe and compliant electrical installation. In addition to the topics covered, understanding the impact of harmonics on electrical systems, the importance of energy efficiency, and the role of emergency power systems can enhance the overall safety, reliability, and sustainability of electrical installations. Firstly, harmonics are distortions in the sinusoidal waveform of voltage and current. Harmonics are typically caused by nonlinear loads such as electronic devices, variable frequency drives, and LED lighting. Harmonics can cause a variety of problems in electrical systems, including overheating of transformers and conductors, increased energy losses, and malfunctioning of sensitive equipment. The NEC addresses harmonics by requiring the use of harmonic filters or other mitigation techniques in certain applications. Secondly, energy efficiency is becoming increasingly important in electrical installations. Energy-efficient lighting, appliances, and equipment can reduce energy consumption and lower utility bills. The NEC includes provisions for energy-efficient design and installation practices. For example, the NEC requires the use of high-efficiency lighting in many applications and encourages the use of energy-efficient motors and transformers. Thirdly, emergency power systems provide backup power in the event of a power outage. Emergency power systems are typically used in critical facilities such as hospitals, data centers, and emergency response centers. The NEC specifies the requirements for emergency power systems, including the type of power source, the duration of backup power, and the transfer switch requirements. When designing and installing electrical systems, it's important to consider these factors to ensure that the system is not only safe and reliable, but also energy efficient and sustainable. Addressing harmonics, promoting energy efficiency, and providing emergency power can enhance the overall performance and value of electrical installations. For example, consider designing an electrical system for a new office building. The office building will have a variety of loads, including computers, lighting, HVAC systems, and other equipment. Firstly, mitigate harmonics. Since the office building will have a significant number of electronic devices, consider installing harmonic filters to reduce the impact of harmonics on the electrical system. Harmonic filters can help to prevent overheating, reduce energy losses, and improve the performance of sensitive equipment. Secondly, promote energy efficiency. Use energy-efficient lighting, such as LED fixtures, throughout the office building. Install high-efficiency HVAC systems and motors to reduce energy consumption. Consider using occupancy sensors to turn off lights in unoccupied areas. Thirdly, provide emergency power. Install an emergency generator to provide backup power to critical loads such as emergency lighting, fire alarm systems, and elevators. The emergency generator should be sized to provide power for a sufficient duration to allow for a safe evacuation of the building. By incorporating these features, you can create an electrical system that is safe, reliable, energy efficient, and sustainable. Remember to consult with a qualified electrical engineer and adhere to the NEC and other applicable codes to ensure a safe and compliant electrical installation. These considerations provide a more comprehensive and detailed overview of the various aspects of electrical installations and the role of the NEC. By understanding these concepts and following the NEC requirements, you can ensure that electrical systems are safe, reliable, and efficient.